Hi everyone, my name is Zhao. My presentation today is a complexity analysis of LabVIEW systems models. We will start with the background, bad smells. Bad smells, also known as code smells, are certain structures in the code that indicate violation of fundamental design principles and negatively impact design quality. Code smell is very common in development practice. For example, one of the most common code smells is duplicated code. As you can see from the example, duplicated code means that there are several pieces of code that execute the same functionality. It's extremely common in practice. For example, when we use paste Ctrl C, Ctrl V, we can find several duplicated code. Duplicate code is not desirable in practice because, for example, if one place has mistakes, we have to revise all the other places manually, which is very easy to forget sometimes. Corresponding to the best smells to system models, we have the concept of model smells, which means the smells in models, like the duplicated code. We have corresponding code smell for models, that is duplicated model parts, as shown in the figure below. Duplicated model parts, like duplicate code, means we have several pieces of model parts that is duplicated. Now we want to define our research with software artifact. In our research artifact is the system models built in LabVIEW. LabVIEW is a system design platform and development environment for visual programming language from National Instruments. The reason why we choose it is because LabVIEW has a large industrial user base. From a note by the LabVIEW manager, they have more than 35,000 customers worldwide. And what's more, the research on LabVIEW models is limited. For example, the research on LabVIEW smells, if we Google it, we only find one related work. So next, we want to introduce the motivation of our study. The existing literature summarized 20 smells for LabVIEW models. So to understand what smells are perceived as prominent from a user's perspective, we conducted an empirical survey to gain deeper insights into what bad smells in LabVIEW are more significant. We sent out a survey to several places, such as the experts in LabVIEW and the end users from the forum posts, and we also sent our survey to the social media such as Twitter. And the result shows that most users are most concerned when the LabVIEW model, which also known as VI, becomes too big. We further asked the users what does it mean when VI becomes too big, and the result shows that when VI becomes too complicated, they think the VI is very hard to understand. So the result, statistical result, is shown as in the figure, and we can see that large VI has the highest mean perception, which means users agree that large VI is the most prominent model smell. But another challenge is when we look into how to handle this model smell, but there is no existing literature on how to characterize the complexity of a LabVIEW model. To solve this issue, we proposed a metric suite for complexity analysis for LabVIEW models. The first metric in our suite is cyclomatic complexity. Cyclomatic complexity is one of the most classical metrics for characterizing the model complexities. So complexity, a cyclomatic complexity deals with the conditional structures in the program, mapping the concept to the LabVIEW models. Now, we are concerned about how many conditional structures in the LabVIEW model. There are four different kinds of conditional structures in the LabVIEW model. That is while loop, for loop, case structure, which is similar to if-else statement in textual-based programming languages, and event structure, which is similar to switch statement. The calculation for cyclomatic complexity is we just add the number of total conditional structures plus 1. The next weight is Halstead complexity. Before introduce this metric, we need to define 4 basic metrics, that is the number of distinct operators, number of distinct data processing blocks, number of total operator flaws, and number of total data processing blocks. And we can define 5 different metrics based on these 4 basic metrics. They are model vocabulary, model length, model volume, model difficulty, and model effort. We will show an example from this to show the Halstead complexity. Suppose we have a LabVIEW model shown in the figure. We want to do some mathematical processing for 2 inputs. Suppose we have 2 inputs, x and y, and we have 1 output after some processing of x and y. So here, R1, which means the number of distinct operators, we have 3. There are 2 inputs, x and y, and 1 output result. And R2 is the number of distinct data processing blocks. Here we have 3 different processing blocks. They are the square block, and reciprocal block, and add block. And A1 means the number of total operator flaws. Here A1 equals 7 because input x has 3 times of flows, and they are from x to the square block to the reciprocal block and add block. The same for y, and the last flaw is their summation to the result. And A2 is the number of total data processing blocks. We have 5 total blocks here, 2 square blocks, 2 reciprocal blocks, and 1 subblock. And after these 4 basic metrics, we can calculate another 5 metrics based on these 4 basic metrics. The next metric is information flow complexity. Here we need to introduce a concept first, that is sub-VI. A sub-VI is a subroutine of a model. It's similar to a function for a program. And another concept is fan-in and fan-out. Fan-in means the data flow from sub-VI into its caller, and fan-out means the data flow from one VI out to its sub-VI. For example, we can abstract the example we shown before to a sub-VI. And after this, we can just do the calculation directly by calling the sub-VI we already defined. Here we can see the fan-in, which means the data flow from sub-VI into its caller, is 1, because the sub-VI here, the square, reciprocal, and sum, it gives out 1 value to the result, and fan-out, which means the data flow from one VI out to its sub-VI is 2, which they are x and y. Here we define the information flow complexity as the equation you can see on the screen, and the example above, the information flow complexity equals 9. Similar, we can also use the fan-in, fan-out, and for another metric, which is card and glass complexity. Card and glass complexity includes three metrics, which is data complexity, structural complexity, and system complexity. The data complexity is defined as the number of system input and output divided fan-out plus 1, and structural complexity means that the fan-out times fan-in, and system complexity means the summation of these two metrics, data complexity and structural complexity. The next metric is cognition complexity. So cognition complexity, which also means cognitive complexity, refers to difficulty to intuitively understand a unit of code. We first define a cognitive weight for each block in a LabVIEW model. The most complicated blocks are for loop and while loops, so they have a cognitive weight of 3, and the other two structures, case structure and event structure, they have cognitive weight of 2, and function calls, they have cognitive weight of 1, and all the other structures, we didn't assign any cognitive weight to them. For example, and the cognition complexity calculation is defined as the summation of all the blocks. For example, from the example here, we can see the cognition complexity. First, we can see there are two parallel structures. One is a square block, and one is a loop structure. And the cognition complexity of a square block is 1, and the while loop is 3. But inside while loop, we have another 3 blocks. So there are an event structure, a loop, and another square block. So we sum up the cognitive weight of these structures too. So far and so forth, we get the final cognition complexity of this program as 19. The last metric is user interface complexity. LabVIEW offers user interface for the block diagram we built. For example, the example we showed before, the square, reciprocal, and summation example. The user interface for this program is shown as a figure below. So when we give the input x, y to the user interface, we can see the result from the results on the user face directly. For example, we define two interface complexities here. One is array size, another one is density. For example, from the user interface we show here, we can see there are two elements on this user interface. The first element has a weight of 20 and head of 10, and the second element has a weight of 50, head of 8. And the screen width and head is 220 respectively. And based on these basic numbers, we can get the array size and density by doing simple mathematical calculation. There are two future directions based on our study. The first one is we want to theoretically validate our metrics. And the other one is we want to do some empirical evaluation for our metrics. For example, there are several existing open access LabVIEW models that we can use to evaluate our metrics to see whether the metrics we proposed could characterize different complexity aspects for a system model built in LabVIEW. If you have any other questions regarding this research, please feel free to contact me at email address shown on the screen. Thank you.